Okay. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Ready? So the plan is as follows. Today, have you seen the announcement? I think there was an email sent with the plan. Yeah, about the midterm. So midterm will cover all of the material till last lecture. Today's lecture is supposed to be just a small extension of of what we saw last time. Hopefully, it will wrap a lot of stuff together. If you already studied, inshallah, you'll find today's lecture, just tightening a little bit of the information that you've seen. If not, then you should consider this lecture just as the bridge between the stuff that you'll be studying, considered so far, and when you start working on the project. Okay, so that's why in the last part, inshallah, we're going to be discussing the project, what you should be delivering, and you should start to, after midterm, you should start getting your team and to discuss together what's your plan to do this to fulfill all of the requirements of the project. Today, inshallah, I'm going to show you some code. So everything we discussed so far, I'll show you how it's put together in a code. You'll have this code at home, so you'll the purpose is not to go in details of through the code, but just to give you the main idea and how you should be delivering something similar to it in your project. Okay, not in one go. So I'll show you today the whole thing in one go, the modeling and the simulation. When you should be delivering the project, you'll have the modeling part alone, simulation alone, and the control alone. So there will be 3 phases for the project, but that for later. So let's start with the lecture. So let's see. Okay, should see lecture. Okay. So recap of what we discussed so far is that we looked at the forward kinematics and the differential kinematics first. So the forward kinematics was the map from all of the configurations, the configuration joint angles or the joint configurations for each link. So every joint that's connecting 2 links together, in the end, how it maps to the end effector pose. So how is the pose of the end effector relative to the base of the robot? And we saw that using the exponential map of SCE3 is given simply by the product of exponentials formula. The only piece of information that you need to provide here is the home pose of the end effector relative to the base and all of the screw axes of each joint relative to the base as well. Okay, so all of the S's here, they are constants. The H from E to 0 is also another constant. You plug all of these constants together inside of this formula, it will give you in the end the end effector pose relative to the base. Okay? Just one line in the code as you're going to be seeing today, inshallah. The differential kinematics is the differential of this map, and it was given from Q dot to the end effector twist. And we said that this map is given by the geometric Jacobian. The geometric Jacobian is 6 by n matrix, where every column of this matrix, you'll find it has this shape. So if you look at the ith column of this matrix, of this geometric Jacobian, it will be something like this, which if you look closely, you'll find in the end it has nothing else than simply the constant screw axis that we already defined, that we already used in the forward kinematics, and they're just plugged in this equation that has that joint. Okay, and then you have the joint of E of the first joint, the second joint, and so on up till the ith joint. Okay, so this was the equation for the geometric Jacobian. And in the end, we have this very systematic approach that we just need to provide these 2 pieces of information, and it will plug in this forward and differential kinematics, something you can program. Hopefully that I'll show you today, inshallah. And what you get out of it is the end effector pose and the geometric Jacobian relative to the 0 frame. If you want to represent it in the end effector frame, this is a very important matrix. You're going to see why today. If we need to transform this one to that one, you just multiply by the adjoint from 0 to E, and we already calculated from E to 0 through the forward kinematics. So then we looked at, so what we did in the kinematics part is that we only needed 2 frames, one at the end effector and one at the base. Then when we wanted to go to the dynamics, we need to introduce all of the intermediate frames. Okay, and thus, if we want to look at the pose of the ith link, it will be given by this expression, which is exactly the same as what you saw. The only difference is that we're doing the product from 1 up to I. So that from 1 up to n, including the end effector. And the same also for the ith, the body twist of the ith link. It will be also given by a 6 by n matrix, which would be exactly the same as the one that we had, so exactly the same structure as the one for the end effector, except that the last n minus I columns will all be zeros, and they're going to have the first I columns there, and they will also be represented in the ith frame of expressed in the I frame, which is the body fixed frame of the link you're talking about. Okay? Which is again something very simple that we can simply compute, because we already have from I to 0 that we computed in this form. Okay, so we're just adding more information. There are the body fixed frame here given to every link. There are no requirements on it, which means that it doesn't need to be at the center of the mass. It doesn't need to be at the joint location of the parent. It doesn't need to be at the joint of the child. You can put it anywhere. However, the convention, okay, is that you can either put it at the first thing, because you have this choice. All of the math that we had is independent of where you represent it. If you remember when we looked at the rigid body equations, they were valid whenever you represent the body fixed frame, no matter how orientation it had, no matter where it was placed. So we're not bound by the math. The math works for any choice. So the usual choice is that you're either going to put it at the joint itself. So you're going to put the ith frame at the ith joint, or you put it at the center of mass. The reason why you choose one or the other, actually, in practice, when you're working with, you have the freedom to put it on both usually. Okay, and in some cases, the joint axis will be represented easily when you put the ith at the joint, and the moment of inertia, so the generalized inertia matrix will be easier if you look at the center of mass. So that's the reason why, okay, usually you look at both. And when we go to the code, you'll see this implementation, inshallah. Then when we wanted to talk about the dynamics, so this was the first component. We needed to add the links. If we want to go from the kinematics to dynamics, we need to add frames at every link. That's the first thing. The second thing, we need to look at this idea of the wrench and twist duality. We said that for every joint, we have this map from Q dot to the relative twist, and thus the dual of this map, which is the transpose of this S, will map the wrench, the constraint wrench to the constraint torque, and to the activation torque. So this is if you have any activation. If not, then this will be just 0. And in the end, you have that when you pair the wrench with the twist, it will be equal to the twist multiplied by the Q dot. The same expression, this idea of duality is very powerful. It works even when you look at the map from Q dot to the ith twist. We also can look at the transpose of this map. The dual of this map will map from the ith, any external wrench that you have applied on the ith frame, and it will be mapped to a torque that corresponds to this, okay, wrench. And in the end, also, if you pair these two quantities and these two quantities, you get this power balance. So it just follows naturally from the power balance. You're going to see why these equations are very important. They will appear a lot today in the dynamic equation. And then we discussed last time the parent-child dynamic model. We just look at we said that the serial linkage in the end is nothing else than two links connected together through joints. We don't have any kinematic loops. We just have one link connected to another link, and there are just joints in between. So we have this serial linkage. It's an open chain. So for every parent, we have an equation of motion that looks like this. For every child, we have another equation of motion that looks like this. So this is just the equation of motion of the rigid body. Okay, you should be familiar with this by now. And in between, we have a 3 set of equations we derived last time. So we can you remember the intuition behind them is that they constrain the two equations. They limit the number of degrees of freedom. If you have two rigid bodies that are not connected, then the first rigid body has 6 degrees of freedom. The second rigid body has 6 degrees of freedom. They're free to do whatever they want. If you connect them through a joint, you already lost. Okay, you already constrained. If this is a 1 degree of freedom joint, you've already constrained 5 out of the 12 degrees of freedom that both had. Okay, so these 3 equations, they say nothing else than you've constrained these equations. When we repeat all of this, yes, Norman. Or like the double. So this model alone, this dynamic equation alone, was 6 degrees of freedom, right? If you remember, the twist here was 6-dimensional. So this means that you have 6 degrees of freedom to change. The same here. So when you put this whole block, which is denoted here by D for reasons I'm not going to go into. So these 3 equations themselves, in the end, they will constrain. So we had here 6 and 6, which means I had 12 degrees of freedom. How many of them are constrained?
5 and 5. 1 and 1 will be auto because of that joint.
No. What you will have here is that you're only going to constrain 5. You can think about it this way. So the parent is allowed to do whatever it wants. Okay, so it has still the 6 degrees of freedom. And this child, it had 6 originally, but because I connected it by a 5 degree of freedom joint, I lost 5 of this 6. So how many degrees of freedom does actually the child have?
The child will get it.
Both of them. So the dynamic equation doesn't care about who is, who's affecting by who.
It's kind of like practically, if you pull the joint, so the motion of child will be restricted by that. The movement of parent will not be.
The reason you need to think about it is that there is actually no thing. This is actually called a causality. Who actually is the parent? Who is actually the parent and who's the child is not actually clear. I'll give you the example. Take the 2 links and throw them in the air. They are connected by the joint. Who's leading who? Exactly. So that's the thing. So actually, the child can normally be the parent and vice versa.
If you throw them in the air, now they are constrained by that joint, so they will be only having 2 degrees of motion.
No, the parent itself will actually have 6 degrees of freedom. It can do whatever it wants. And as a consequence of this motion, the child will have only 1 action.
They are not fixed which is parent, which is child.
No. Okay, that's the idea. If you constrain the parent also by another joint to maybe a fixed link, how many degrees of freedom do you have? So I had 12 originally, and then I constrained here 5, and I constrained with another joint 5. How many left are you left with? 2. And we call this a 2 degree of freedom.
This is what I
a 2-link manipulator, right?
Thinking fixed on the ground and then.
No, they were both. You throw both in the air with this. Okay. So if you repeat it, if you do this recursively, in the end, you're going to find that I can add n rigid bodies connected by n. I'm going to have n plus 1 rigid bodies connected by n joints. If I connect the parent, the first one, to like a fixed base, we're going to have what we call a fixed base manipulator that has only n degrees of freedom that we have. So this is the picture, okay, for the 2-link manipulator. And in the end, we're going to have a set written like this. What we have is a set of differential algebraic equations. You can take them as is, and you can directly simulate them. There are software tools that allow that. For example, this is exactly how you do it in Simscape. Okay, so if you're using, for example, Simscape, this is how you build it. However, when we want to do control, we don't actually work with this implicit. This is usually called an implicit model, okay, because it doesn't have, input plus something equal to differential equation explicitly. We need to get rid of the constraints when you're solving for them inside of the code. But then we want to reduce it we'll find what's known as the reduced dynamics. So the reduced dynamics will be a set of ordinary differential equations that we can work with and we can do control. Today, I'm going to show you also, hopefully in the code, how you can actually simulate this. It's very easy to simulate this. It doesn't mean, by the way, that this is actually, you're going to get better results. It's just, it's easier to look at because, you get more, you get less stuff here. So if I have, if I have 2 rigid bodies, I have 12 equations and, 10 constraints. But here, I just have 2 equations that describe the system. So it's easier to work with and to reason about. The process that we went to go from this differential algebraic equation to this reduced model was called the recursive Euler-Newton formulation. So, recursive Newton-Euler formulation, RNEA, recursive Newton-Euler approach or algorithm. And we shown last time, so it was a lot of recursive equations. I showed you in the end how you can just compactly write them in a very elegant form in these 4 equations. The first one is will tell you how all of the joints, the V here consists of all of the body twists, how they are mapped to the Q dot. So we had this big matrix L multiplied by S. And the V dots, I can simply compute them in an expanded form. I think there's No, it's correct. Yeah. No, it's correct. So we have this expression, and then afterwards we have this equation, okay, which is for the wrenches, which consists of, you see here, all of the inertias, they appear here because this is actually nothing else than the rigid body equation, but just stacked over each other. And I have here all of the constrained, all of the actuation torques that come from this constrained wrenches. And you see, I can eliminate now the W and all of the V dots and the W, I can eliminate all of them. And in the end, you're left with an equation. So these are all of the expanded forms. They're just equations that you can recursively implement in the computer or just implement them like blocks like this. And in the end, we've shown that we reach this reduced set of equations that are in the end, if you see the dimension of this is a n by 1 vector. Okay, vector as in, tuple. This is an n by 1 tuple. This is an n by n matrix. This is an n by n matrix, and you're left here with the n by 1 control inputs. So this is actually the dynamic equation for an n-link manipulator. The M was given by this expression, and the C was given by this expression. The M is known as the inertia matrix or the mass matrix. The C is known as the Coriolis and centripetal matrix. The reason why it's called the Coriolis and centripetal matrix is that if you start to expand all of the terms inside, you'll see that they just correspond to the Coriolis forces and centripetal forces that you would usually have in a mechanics setting. Okay? So if you already have any mechanics course, you can trace back, you can take any simple example and see how this C matrix look like. If not, then you just see this is usually how it's called. So this is where we stopped. This is what you should know for the midterm. How you're going to be asked about in the midterm, we can discuss in the end, inshallah, if you want to know, if you want to know how to study. But if you understood everything I said so far, this means you're already well prepared, inshallah. What we're going to be doing now is two things, for in this lecture. And you see how they immediately, they are just missing parts for the dynamics. And this is what you need to do for the project or for any real application. We need to add external wrenches. We haven't discussed any external wrenches. I'm going to show you now how we can easily add them in this formulation. And I'm going to show you, inshallah, some software implementation. How all of this fits together in the software very easily in in one MATLAB code. You can simulate this for any robot and you can see it, how moving and so on. So this equation, which is now the dynamics for an n-link manipulator, is given by M of Q multiplied by Q double dot plus C of Q and Q dot multiplied by Q dot is equal to all of the taus that are applied at the joints. So these are the actuation. So now we have an equation that describes all of the torques applied at the joints and how the joints change. They are missing here any torques that are due to the interaction at the end effector. So usually if I have the end effector, for example, I'm drawing or pushing or doing something with it, then I get some reaction torques. How do we model all of these torques? So that's one thing we're going to look at today. How do we include these external wrenches? And another important thing is gravity. We have here, this robot we haven't talked about gravity at all. So how can we include gravity into the game? So these are the two things we're going to be doing. But first, let's look at how do we actually, if we have an external wrench applied at any one of these joints, how can we easily include it into the formulation? If you go back to the recursive Newton-Euler approach, you'll find that when we wrote the equations, we actually left out a term here that corresponds to all of the external wrenches. So very easily, if you add these external wrenches, you're going to find that what will only be changing is that we're going to have this extra term L transpose multiplied by the wrenches external. Where this wrenches external is also a stacked, very big, vector that will have the wrench external applied at the first link expressed in the first links frame, the second wrench, the wrench external applied on the second link expressed in the second links frame, up to the wrench applied on the nth link expressed in the nth links frame. So this is the piece of information that was missing. If you repeat exactly the same stuff, you see, I'll just show you how easy it will be. If you remember this equation, we took it and we plugged it in here, right? So we had an S transpose multiplied by this, S transpose multiplied by that, and S transpose multiplied by this. S transpose, L transpose. Does anyone remember what we called it last time? The L multiplied by the S together. We called it what? The S multiplied by the L multiplied by the S, we called it the J matrix. It was this huge matrix that had Okay, it was just the L multiplied by the S. The S itself was block diagonal, and the L was a very huge matrix. Let me remind you with it. So this was the S, and this was the L. Okay, so if you look at the S, it was just a block diagonal of all of the screw axes that we have for every joint, expressed in the links frame. Okay, so usually it's expressed in the child frame in this S, while the L here, okay, is given by this matrix that has all of this block identity matrix at the diagonal, and it has here just adjoints. Okay, for every from 1 to 2, from 1 to 3, and from 1 to n, and so on and so forth. Okay, so you can build this L, you can build this S, you multiply them together, you make this J. So here, what appears in the equation, the only thing that will differ is that the equation M of Q, Q double dot, plus C of Q, Q dot, multiplied by Q dot, will be equal to the tau, which is the activation, plus the J transpose multiplied by wrench external. That's it. Okay, it's very easy. But be aware that this J actually, this wrench includes all of the wrenches applied at every link. Okay, it's not necessary that I have an external wrench at every link. So in that case, you can just remove them from the equation. There is here a second equation. When we say the ordinary differential equation is only this part. Okay? This is usually an output equation. I'll repeatedly show this output equation here because I want to make a point here that you'll always find there's an issue of duality here. That this equation has an input, the wrench external. As an output equation, you find that we have the V, which correspond to all of the body twist, okay, for every link. Okay, and it's related by the J. So if this here, there is a J transpose, there is a J here multiplied by the Q. Okay, so this equation, we don't need it to solve the equation, but you can have it as an output equation. Okay, and I'll show you, you'll find this recurs, this is the recurrent equation that will appear a lot, this output stuff. So this is the equation, that's it. This is how you do external wrenches. What we're going to be doing now is let's take a closer look at the J. The J is a very special matrix. Okay, if we take a look at special on it, so this is how you expand the two matrices together. This is simply the L multiplied by the S. The S itself was just block diagonal. So the only thing that and the L itself had at the diagonal all of the identities. So the only thing that will change is that the J here will have at the diagonal will have the S's, but also the S's will appear here. Okay, in these equations. It's very easy to actually take a 2x2 expression and just work it out and see what happens. Okay, so these expressions, the only way really to understand them is that, you know, take a 2x2 example or 3x3 example and just work them out. See them once for your, you know, for your life, and then always, you know, program them at this generality. Okay, because it's just too much to take at one shot. Now take a look at a closer look. If you studied, okay, and I doubt that, so you'll find that every one of these rows is actually equivalent exactly to what we called the ith geometric Jacobian, okay, expressed in the ith frame. Okay, this you need really to go and study and to compare stuff. For now, you can just take my word for it that actually each one of these rows is actually, so this whole J was, its dimension was 6n by n. So for every one of this, every row of it is actually 6 by n, okay? And then we have n of these. So I have 6 by n, okay, matrix that looks like the J here. So I just have J100, J101, J202, J303, and so on up till Jn0n. I just have all of the geometric Jacobians stacked one over the other. And this is exactly the J that we have here. For each link. So we're talking about this J. If you go back a little bit, this J. Yeah. And you remember we said already it had a lot of zeros. We said that here from I plus 1 up till n, we had zeros, remember? In this J. Take a look at here, just as a sanity check. From I plus 1 till n, I just have zeros. So that's in the first one. And then here, all of these will be zeros up until, the only one that will be filled is just the last one. And the rest are just, you know, the zeros. So they are exactly the same. which means actually the J of Q, which is this very important matrix that appeared a lot here. If you go back to this expression, okay, which one? This expression, you see the J appeared a lot. So there's a J transpose, the J transpose, J and J transpose, and J and so on. So it appeared a lot. This matrix is nothing else actually than this huge matrix is just the collection of all of the geometric Jacobians. So again, the geometric Jacobian, you see how important it was and how it makes our life here easier to actually do all of these expressions. So this is the J of Q. And just also as a check for yourself, that's something we did last time. You remember we showed two expressions, actually two definitions of the mass matrix. If you already studied this part from last lecture, we showed that the M of Q is given actually by this expression. But if J now is all of this stacking of all of the geometric Jacobians, and the I itself is nothing else than just a block diagonal, then it's very easy to check that in the end, the mass matrix is just recursively, okay? I can calculate it by this expression. I only need to multiply this one transpose by this one, okay, multiply by this one. Okay, there are no cross couplings because of all of this block diagonal stuff. Okay, so in the end, you see that the mass matrix, instead of calculating it by this huge matrix, I can calculate it recursively like this. By the way, they say the same actually you can do also for the C matrix. You can actually compute it recursively, and this is actually one of the tricks that you can have an efficient implementation of this in software, okay? Because these are very heavy, to calculate and to store, but doing this actually recursively is actually, it is very efficient to do in code, okay? So this is the whole idea of the J. So now if we go back to the equation where we looked at the reduced dynamic equation, when we had all of these external wrenches, we simply have this expression like this, okay? We have the J of the 1 transpose multiplied by wrenches external at 1, J2 transpose multiplied wrench 2, and so on and so forth, up to the nth one. And as an output equation, for every one of these external wrenches, we have this output equation that corresponds like this. Okay? So this is how you do external wrenches. Easy? Okay, very easy. Now let's look at two special cases. The first one is that, what if we have the robot doing something, okay, interacting with the environment? So when it's pushing on the environment, what does the environment do? It pushes back, okay? If it tries to rotate the environment with a moment, what does the environment do? Apply a counter moment, okay? In general, we say that if the robot is applying a wrench at the end effector, it's applying a wrench at the end effector to the environment, what will the environment do? Apply a wrench back, okay? So this wrench back is called here the wrench of the tip acting on the end effector expressed in the end effector frame. What are the corresponding torques that come from that? Simply just multiply by the J transpose. You get this, okay, expression here. And as an output equation, we just have the twist at the end effect. Easy? Okay. Make sense? So that's for the end effector interaction. What about the gravity? Any ideas how we can use this stuff to actually do gravity? Exactly. So we can say that every link, there is actually a wrench that tries to do what? Pull it down. So here I'm going to have a wrench at 1 due to gravity, wrench at 2 due to gravity, and so on and so forth. Okay, and then I transform all of this by the J transpose, and I'm going to get an expression here for the gravity. As easy as this. Just some caveats. What is the wrench due to gravity? You've never thought about a wrench due to gravity. You only know about what? No, forces due to gravity. So what is the force due to gravity? Exactly. Only at the center of mass, you can talk about this. So the equation for the gravity, so if this is the equation for the gravity, so if here, take a look at this frame. If this is how we chose, for example, the body fixed frame, we chose it to be at the center of mass, aligned like this with the robot, okay, with the first link. And we chose here this frame to be aligned with the second link like that. How is the gravity applied? Can we say that gravity is just a force in the Z direction of two frame? Exactly, needs to have components, right? You don't, of course, you see, if you think about components and sine and cosine, you're already, okay, you're not using the tools of the course. If you want to use the tools of the course, simply define the gravity, okay, as so define MIG, okay, which is the gravity seen in the zero frame, okay, but applied at the center of mass. And what do you do to this force? You just multiply it by the rotation matrix from 0 to I. Okay? Then you transform, actually this rotation matrix from 0 to I will already do the sine and cosine for you. As easy as this. Do I need to explicitly calculate R0 from 0 to I? Or we already calculated in what we were doing before? Which part in the kinematics did we calculate from R0 to I? So when you look at the rotation matrix that you need this information, it came from the H, it came from the homogeneous transformation from 0 to I. And the 0 to I came as the inverse of from I to 0. When did we calculate the H from I to 0? At which part? If you go back, where was the expression that calculated for us the H from I to 0? You'll find it was actually this expression. We did not do it at the kinematics level. If you remember, we said that at the kinematics level, we did not need to introduce any I-frame. But since we, as an intermediate step to go to the dynamics, we needed to add all of the I-frames here. So when we did that, this is the expression that will calculate for you from the H from I to 0. And you can do it for the link 1, link 2, link 3, up to link n. Okay? And then you take the inverse of it. You don't need to take the inverse. You just take the R transpose and minus R transpose multiplied by design. So even there is no even in matrix inversion at all. So this is how you include the gravity. So this is how the gravity is applied at the ith link expressed in the ith frame, provided that there's a big here, exclamation mark that you need to beware of, which is I is placed at the center of mass, exactly. Okay, so this is very important. So this is usually how the gravity wrench looks like if I is at the center of mass. Okay, so now you see, yes.
Some aspects, it's, for example, for the End-effector, it's easier to place it at the link. We talked about when we are trying to express the links.
Yeah.
It's easier to place the frame at the link. We can place it anywhere.
That's right. You're talking about placing at the joint. At the joint, yes, exactly. Yeah.
How can we have the frame placed at two different places?
That's a very good point. So now we said that we need to choose a place where the ith frame is located. Let's go back to this slide. So we need to choose a place for the I frame. How can we choose two places now for the I? The reason is that the way you do it is you just choose one. Okay? You just choose whatever you want. There is a convention, for example. If some software tools, they already assume that you've put the frame there. And thus you never think about it, but you need to, if you really want to do something with it, you need to know which frame you're talking about. Usually it's placed at the joint. And then intermediately, you can add another frame at at the center of mass, and then do the calculations there, and just use that joint to transform all of the quantities from here to there.
The gravity, we are doing it sort of offline. We are doing it separately.
That's right. Yeah.
And then putting it back into the algebra.
Exactly. So you can put this intermediate frame at the center of mass and then transform. Or easier, there is actually a formula that you can actually do that. I'm going to show you now. There is actually a formula that will work and will give you the gravity wrench applied at any location, not just at the center of mass. So there is a much more elegant way to do it. That's exactly what I'm going to show you right now. What's more importantly than the joint link is than actually the gravity is the inertia itself. The inertia matrix, usually you say it's just, it's just a diagonal, maybe J, and then you have a mass. This is only valid where at the center of mass and also have with the center or with a specific orientation. If you build your robot and you take, for example, the link and you go to SolidWorks and you tell it, give me the inertia of this body expressed in my frame of choice, which is, for example, the one that you place at the joint, it will give you exactly the full 6x6 matrix, or at least the pieces that you need to build the 6x6 matrix expressed in that frame directly. Okay, so it will tell you the center of mass location in that frame. It will tell you what how the inertia matrix, the J, looks in that frame, and the mass, of course, is just a constant. It doesn't care which frame it is. Okay? And then you can use this information to build it. Okay, so the bottom line is it's easier actually just to put it at the joint. Okay, and just transform everything. Okay, when you define it there. Okay? Now go back to the gravity. There is a much more elegant way to actually do the gravity than to do it like this, okay? Before that, let me show you a more familiar way that you're going to be looking at this equation. You see all of this equation, all of these terms, usually they're not written like this, they're written on the other side, because the gravity wrench here, you see it's just a constant, okay? It depends on the R and the M, and the J here depends on the Q. So you can take all of these expressions, okay, and you can put it on the other side, and usually they're just called G of Q. Okay, so you find that this is actually the more familiar equation. M of Q, Q double dot, plus C of Q, Q dot, multiplied by Q dot, plus G of Q. What's inside of this G of Q? It's simply the J minus the J transpose. This J is the big one, okay? And the gravity wrench here is the stacked one for gravity acting on H length. Okay? This is the expression that we just derived by looking at the gravity as an external wrench. There is an equivalent way of doing gravity. Okay? It's not familiar, okay, usually, okay, in engineering, but here if you apply this, okay, concept, which is well known in physics, you're actually going to get a very elegant way of representing gravity. And this is usually known as Einstein's equivalence principle. Okay, so this is only for your eyes, okay, to look at once, okay? You need to dive a little bit into this stuff if you want to understand it more. But the whole idea is the following. So instead of looking actually of gravity as an external force applied to the body, it's like a force that's, you know, pulling the body down, we can understand gravity as actually that there is no force applied on the body. It's just that the whole world is just moving up. This is gravity, okay? Exactly. Our entire inertial frame is moving. That's exactly how it is. So we're going to be instead of looking at, I have a fixed frame, instead of, I'm saying that, okay, I have that the inertial frame is fixed everywhere, okay? And then gravity is just pulling us down. We can imagine that actually the whole link is nothing else than just free falling in space. And actually, if you think about this, exactly how it is. We're actually in free fall right now, okay? We and Earth, okay? We're just free falling, okay? But usually, of course, you never think about it, okay? And Einstein's equivalent principle is summarized as the following, okay? This is how it is in words, that there is no local experiment that can distinguish a uniform gravitational field from an accelerating reference frame. To rephrase this, imagine that you have this box that you live in, this room, and you take a ball and you throw it. What happens to the ball, this apple? It goes down. This is a Newtonian way of looking at it, right? There's, you know, gravity pulling us down. Another way of looking at it is that if you take this person, put him in a rocket, and let this rocket accelerate, and then he throws the ball, what happens to it? It falls down in exactly the same way. So there is no way that you can actually tell we're fixed or are we accelerating. There is no physical experiment that can actually distinguish these two.
It's to be exactly the same. The movement and the speed of the acceleration have to be the same as the one we are considering for the.
Absolutely, yeah, absolutely, yeah. You just need to have constant acceleration, which is simply how you say here, gravity is simply 9.81 or 9.8 something, you know, meter per second square, downwards. Okay, this is the gravitational acceleration. And otherwise, if you get on this rocket and it goes with 1 g up, you find exactly the same wave. Sorry? No, it will float if you're not accelerating.
Constant acceleration of which is equal to the gravity in the negative direction of gravity.
Yeah.
Will it float?
No. I've only put this for you to think about it, not to. Exactly. One of the things that actually they do on the space station, exactly, they make it move and then you get gravity. It's not artificial gravity. It's actually, it is gravity. It is the exact, what this is actually saying, it is gravity. Okay? It's exactly the same as gravity, provided that you have the same numbers, of course. So the bottom line, of course, I'll not go into details here, but the G of Q, we can very elegantly write it as an equation like this. Assuming it's J transpose multiplied by all of the inertia multiplied by the L we calculated, multiplied by a V dot of the base. We assume that the base of the robot actually is just accelerating, okay, up. And this v dot of base will have something that looks like this. Okay, this is only for your eyes to actually see, or just implement it in the code and see where it works. Okay, so you really need some time to look at this.
Then we have to include this component only for the base. We don't have to include it for the other.
Absolutely, yes. You have to only include the v dot for all of these terms.
Counterintuitively, if we are moving, let's say, I understand that if we consider it to be moving upward, there will be, let's say, another force acting on the base of the rope.
Yes, exactly.
It's also acting on the limits.
Through the constraints. So it's not actually that the links that are changing. It's actually that the reference frame is the one it's not the base, it's the reference frame. The inertial frame is moving, is accelerating.
Then it's the same thing. If we consider that the link is fixed, for example, if we are fixing it to the earth,
yeah,
then why we are having it on each link? It should be only a summation of let's say the gravity on one of the links, and then we consider it to be moving downward.
No. So I see your point. It took me a while to get my head around. So you have full right to get confused. So the thing that's actually accelerating here is the inertial frame, not the zero, not the first link. It's actually the inertial frame. When you say that the inertial frame is fixed, then you have the gravity acting as a uniform field. It's not actually a link. It's not actually a force at a link. It's actually a field. You have a gravitational field everywhere, and the gravitational field is pulling everywhere. So you're not saying that the base itself is the one that's accelerating. It's actually the whole inertia. It's like the whole world is actually accelerating.
Zero, there is no force. Now
Yes.
Force.
Exactly. Okay. Okay. You need to think about it a little bit. Okay. That's the bottom line. So we're done. So that's the yes, right. That's an excellent question. Why do we need to look at this general way of looking at the equation when we can have this more intuitive way of writing gravity? Any reply to that? That's okay. That's one. So the formula is simpler. That's one. But what else? What is actually easier here? How is the other equation more general than this one? No.
Other reference, other inertial frames as well.
You don't need to do that. No, but just from an engineering perspective.
Fixed base or moving base, I think, because we're moving the inertial frame.
No, it doesn't matter. Yeah, exactly. It doesn't matter. No. No, doesn't need. It's very easily that this expression for calculating this, for using this expression here, okay, to multiply by the J, where is it? To actually multiply by the J transpose assumes that you're already choosing the ith link at the center of mass. So if you want to do this idea of putting the ith link at the joint, will not work, this expression. You need to transform it again by some adjoint transpose from the ith frame, which is here the center of mass ith frame, to the joint ith frame. But this expression works seamlessly in both. Okay, we did not make this assumption at all. Okay, clear? Yeah. Yeah.
At this moment, when we are looking at gravity in another way, we are assuming that the entire forces, which we were assuming in the inertial frame, the fixed inertial frame, we were assuming that we had at each link.
Yeah.
Right? We can also find, for example, in the second method, we found for a force that's accumulative or that's equivalent to all of the other forces. That's now just acting at the base. In the Einstein's way,
okay, yeah.
we have found the right word for it, equivalent force that's now acting at the base, right? At the base of the robot.
No. It's much easier to do what? Take this I, this L, and this V dot and expand them. See what do you get here? You're going to actually get a wrench at every link.
We can do it this way. We can do it the other way for a fixed inertial frame. We can find an equivalent wrench that's acting only on one of the links. Let's say the end-effector. Rotational matrices. For example, R, we will have to find an R that is able to transform it from
no.
the n minus 1.
Yeah, I see your point. No, the fact that actually all of these are zeros here is only because it only affects this v dot expression. So it's actually it only captures here the acceleration of the stationary frame of the inertial frame, and the L here is actually coupled. Okay, it will couple all of this together, and the I is actually block, and the J here was actually, will take all of this stuff, and you're gonna find that we're actually this expression will be equivalent to minus the gravity wrenches that we had here. So in the end, you're gonna get exactly the same number. It will be just transformed in the generic frame that it shows. So, but this expression written like this was only valid for the center of mass frame. It's best to actually work it out and see it for yourself. Okay. Clear? So that's it. So this is everything you need to know about the equation of motion for an n-link manipulator. This is valid for any link, any n-link manipulator. 10 links, 20 links, you call it. There are just some assumptions here. What were they? We're talking about a serial chain, no kinematic loops. There are no parallel parts. What else did you assume here? The base is what? Fixed, not moving. Extending this from the fixed base to the moving base is actually easy, but at this point, in the course, students get very saturated with the modeling and they want to do control. So if there is enough time, we can go back the last lecture, hopefully, inshallah, can go back to the floating base manipulator, and I can show you how we can extend these equations following the same formulas, okay, to get something that has, a moving base, okay, but that's for later. So this is the inertial effects, the Coriolis and centripetal effects, the gravity effects, actuation. And then you have here anything related to end-effector. Before simulating this, you need to fill in the gaps. So everything here about the reduced dynamics is just defined by the M and the C and the Q. Sorry, the M, the C, and the G. And we calculate this based on this, all of this huge formulas that I showed you that you can just program in once and you can get the M, the C, and the G in a closed form. How software tools they do it, they actually don't compute the M and the C and the G symbolically. They actually compute them numerically. For example, using the summation formula I just showed you. So you can actually do it in a very efficient way. What you need to satisfy, what you need to provide here are two things. You need to provide the controller. So what are the taus here? What are the control torques? Depending on what do you want to do with the robot. So that's something we're going to look at after the midterm, inshallah. And if you want to do something with the robot, for example, to push or pull or to draw or to do something more complicated, like pick and place or more complicated stuff, you need to model all of this stuff. So you need to close the loop here. So you need to have this end-effector wrench, end-effector twist, and you see how it will be modeled, how it will correspond to this end-effector wrench that's applied. So you need to provide this. So now let's go to the software implementation. And now, hopefully, if we have time, I can show you, okay, what you should take from all of this to do in your projects. Question? Yeah.
Based on this general equation, the only thing that will be changed will be the joint and the fixed base.
That's right.
We can assume it as an open joint and then
Absolutely.
simpler. I don't think anything newer will have.
Let's see. Okay. The
base will be less.
it's not about so it's exactly what you said. Yes, of course. So the only thing that will change here is that we're gonna have one extra link, okay, which is instead of saying that the parent link is actually fixed, the parent link will moving, okay, and then if it's moving on the ground, we say okay, it's connected by a planar joint. If it's moving, okay, in the air, you say it's connected with a floating joint. So you see, it should be easy, right? It's not, okay. Okay, you get very, very wild geometry. Okay, the geometry here becomes very, very rich. This is actually a very much area that's not, researched. And I currently have 2 PhD students that are looking at it, and there are 2 more that might join. Okay, okay. So it's a very rich area. Okay, what is the geometry? Again, there is the geometric way and the non-geometric way. The non-geometric way has been a lot of people worked on it. It's very relevant because the floating base robots, they correspond to space manipulators, they correspond to aerial manipulators, they correspond to underwater manipulators, they correspond even to humanoids, to quadrupeds with robot arms, they correspond to anything that's interesting. Robots that manipulators that are on wheels. So all of these are, in the end, they are a big class of floating base manipulators or moving base, a manipulator with a moving base. Okay, and to do it geometrically, there's a lot of stuff to be done. Okay, so if you want, you can do a PhD on it. Okay. So let's see what to do now. So let me show you now the code. So what I will do now is that.
What about midterm?
So you choose now. So I can either show you the. I'll be very democratic. You can either discuss the midterm, or at least let me finish the just the list. You can either discuss what you should expect in the midterm, how to prepare, how you should prepare for the project, which is related to what the software part. So it's either a project or the midterm. We cannot have. I don't think we're gonna have time for. What? The project, the first deliverable will be in the first week after the break.
Later than.
So what do you want? You choose.
Is there an option C where we can type both?
We can do the midterm in 5 minutes, and then we can look at the software and the project.
After the project can be done in the next 8 minutes.
What?
You can beat after the midterm, we're all
Exactly.
together.
Oh.
We will not be, but if we meet on Sunday, which I think will be 29th of March, after we come back, you will have to deliver it on Thursday.
2 days.
No. I know, but
You're generous in that way.
okay, now you're being sloppy. Okay, so let me stop the recording here so that you can say whatever you want. Let's see.